Section 16.7 deals with the acid-base properties of salts. And so if you have a soluble salt and it dissolves in water, the key here is that it will break apart into its cation and anion, and then we need to consider both of those in turn to see whether they have acid-base properties or not. And so let's look at one example. Sorry, ammonium chloride. So this is a soluble salt. When it breaks apart in solution, we are left with NH4 plus and Cl minus. And we'll look at each of these and say, is this an acid, is it a base, or is it neither? And so for NH4 plus, we can see that NH3 is a weak base in equilibrium with NH4 plus. That means that NH4 plus is a weak acid. And so we at least are beginning to suspect that ammonium chloride, when it dissolves in water, will increase the H3O plus concentration and decrease the pH. Now let's look at Cl minus. Cl minus can be said to be a part of an acid-base reaction. HCl will dissociate into H plus and Cl minus. And so that makes Cl minus technically the conjugate base to HCl, but it is only a conjugate base in the most technical sense in this very particular context. Because HCl is a strong acid, you'll notice we have a single-headed arrow here. This reaction does not go in reverse, and that means that Cl minus is not a base at all. So this is neutral. And so the overall effect of ammonium chloride is going to be acidic in nature. Ammonium chloride is an acidic salt. So we can see table 16.4 shows all of the counter ions from strong acids and strong bases that we can assume are going to be neutral in terms of pH. All the anions to hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and chloric acid. Now H2SO4 is one of our strong acids, but remember H2SO4 is a polyprotic acid. HSO4 minus is itself still an acid. And in fact, it's an acid with a surprisingly strong Ka value. Since it has a negative charge, you might think that it wouldn't be an acid at all, or at least an exceptionally weak acid, and it's one of the strongest acids that we have on our tables of weak acids. So anyway, that's one exception to the rule. And then as far as the cations, we can come over here and see that all of the cations that are a part of our strong bases, well, they will also be neutral. And so what this means is that most of our activity is going to be in the anions. A lot of our bases are going to be anions. A lot of the neutral acids will have an anionic conjugate base. The cations are usually neutral, and one exception is, of course, ammonium, which we have up there with this example. And then another example are metal cations that aren't a part of that table that we were just looking at. The metal cations that are not counter ions to soluble hydroxide salts. And so it's a little bit tricky how metal cations can act as acids. But here we see aluminum 3 plus. When it is dissolved in water, it doesn't just get surrounded by water molecules in sort of a, in the sense of most cations where the water molecules just surround it but don't form bonds. The water molecules will actually form what are called dative bonds, and we'll actually cover these sorts of chemical interactions in a later chapter. But they become truly bonded to the aluminum. 6 waters will bond to the aluminum, And then, just as a result of how the electron densities are shifting with the formation of these new bonds, in the context of the larger aluminum hexahydrate complex, one of the hydrogens will actually be released as an H+. And so that makes the aluminum ultimately increasing the H+ concentration. That makes it an acid. And not all metal cations, but many metal cations are at least slightly acidic, and some of them are actually very acidic. So, one moment here. So these are the things to consider when you have a salt and you're trying to determine whether it is an acid or a base. You can have something like NaNO3. Na is one of those metal cations that is the counter ion to a soluble hydroxide salt. So Na plus is neutral. And then NO3 minus is the conjugate to a strong acid, nitric acid, so it is also neutral. And that means that sodium nitrate overall will have no effect on the pH. It is neutral overall. Okay, and we saw ammonium chloride that was acidic overall. Now let's look at something that might be basic. So, lithium carbonate. All right, so here we have the lithium plus, that is neutral. And here we have CO3 2 minus. And CO3 2 minus is a base. It's the conjugate base to bicarbonate, which is a weak acid. And so this is going to accept a proton and act as a base, which means lithium carbonate overall is going to act as a base. If I dissolve some lithium carbonate into pure water, I'll observe the pH going up. The OH minus concentration goes up and the H3O plus concentration goes down. Okay, what if I have something like ammonium carbonate? Right, so we already talked about how NH4 plus is an acid and how CO3 2 minus is a base. So what will be the overall effect of ammonium carbonate? Well, we can get a basic idea by just comparing the Ka value of the acid with the Kb value of the base. And admittedly, things will be a little more complex here because you have twice the concentration of the acid, but these Ka and Kb values are probably disparate enough that just a common comparison of them will do. I actually don't have those numbers, so I'm going to pause it real quick and look them up. Okay, I looked up those numbers. The Ka value for ammonium is 5.8 times 10 to the negative 10th. That makes it a pretty weak acid. And then carbonate has a Kb of 2.1 times 10 to the negative 4th. That's a decently strong base. And so, overall, the base would win. And if you wanted to find actual concentrations and things, well, then you'd have to deal with the complexities of multiple interrelated simultaneous equilibrium reactions. But we can look at these numbers and see that clearly the base is stronger, and the general effect will be that this will turn basic. Okay, now let's look at one last problem. Can we find the pH of a solution that is 0.125 molar in calcium fluoride? If I analyze this, I know that calcium 2+ is neutral, and F- is a base. So I know it's going to be basic, but if I give you some numbers here, can you work out what the pH will actually be for a solution with this concentration? Well, first of all, let's recognize that there are 2 fluorides in every formula unit here. And so what we'll really have is 0.250 molar in F-. And then you're not likely to find F- on a table of bases unless it's a particularly comprehensive table. You're much more likely to find the Ka value for hydrofluoric acid. The Ka value for hydrofluoric acid is 6.6 times 10 to the negative 4th. And remember, the conjugate pairs will have the property that Ka times Kb is equal to Kw. And so the Kb that we're looking for is going to be 10 to the negative 14th divided by 6.6 times 10 to the negative 4th. Let's figure out what that Kb value is. 1e negative 14 divided by 6.6 e negative 4. So we got a Kb value of 1.52 times 10 to the negative 11th. That makes F- a pretty weak base compared to others. Okay, well now we can just proceed with a regular ice table. I know that F- plus water is going to be in equilibrium with HF plus OH minus. And we'll start with the 0.250 molar 0 and 0 here, minus x plus x plus x, x, 0.250 minus x. You do enough of these and you can skip the ice table altogether. I think that is a fair thing that you can start to do in your head. And so what we have in the end is that our Kb value of 1.52 times 10 to the negative 11th is equal to x squared over 0.250 minus x. And we will assume that that x is small, and so we can solve for the value of x by taking the square root of that Kb value, 1.51515151 e negative 11 times the initial concentration of 0.250. I just carried a ton of digits there because it was fun. And I get x is equal to 1.95 times 10 to the negative 6. 1.95 times 10 to the negative 6th. And you may recall that when you're dealing with a base, that is equal to the OH minus concentration. And I find the easiest way to get the pH is to say that pH is equal to 14 plus the log of the OH minus concentration. That's a combination of finding the pOH and then finding the pH from the pOH. You can combine those steps into this nice, slick little equation that I think is really convenient. So we'll say 14 plus the log of 1.946 e negative 6. And we're going to get 8.29. We only get 2 sig figs here. 8.29 is the pH of a 0.125 molar calcium fluoride solution. Fluoride ion has a low enough Kb value that you'll notice this isn't very far from neutral solution anyway. Okay, and that's it for 16.7.